Hello everyone and welcome to the presentation of fitting flats to flats. By the term flat, we refer to an affine subspace of the Euclidean space. That is, for example, a point, a line, a plane, and so on. Fitting a flat to a given set of points is a standard task in computer vision, graphics, data science, and engineering in general. This problem is very well studied, and the most notable solution is the principal component analysis, abbreviated PCA. However, when it comes to fitting a flat to a set of other flats, for example, fitting a plane to a set of other planes, fitting a line to a set of other lines, or even with different dimensions, for example, fitting a line to a set of planes, there is no standard solution for this problem. An example of an application of fitting a flat to a set of other flats is given by the following multi-view reconstruction task of line-like objects. The goal is to determine the position of the arrow on the archery target. The arrow can be modeled as a line, resulting in a plane in the three-dimensional camera space. Capturing the arrow from multiple perspectives results in a set of planes that should ideally intersect in a common line. However, due to noise in the camera calibration, this is not the case. The task here is to fit a line to the set of planes that is as close to them as possible. Current approaches to this problem often lead to the affine Grassmannian, that is, the set of affine subspaces, a smooth Riemannian manifold. The task of fitting a flat to a set of other flats is equivalent to finding the Riemannian center of mass, that is, the point that is minimizing the sum of squared geodesic distances to all given points. Riemannian centers can be found by iterative minimization, but this approach suffers from the lack of translation invariance. For example, while the mean of two lines that intersect in the origin is their bisector, when shifting both lines away from the origin, their Riemannian center is not a shifted version of the previous mean, and thus not their bisector anymore. Also, the theory behind this approach is quite involving, and our approach is easier to understand. Our approach is based on representing flats as squared distance fields, a scalar field that maps every point in space to its squared orthogonal distance to the flat. As it is a quadratic polynomial, it can be represented with a symmetric matrix containing the quadratic terms, a vector containing the linear terms, and a scalar. The matrix encodes the dimension and orientation of the flat, while the vector and scalar encode its displacement from the origin. As the scalar can be directly computed from the vector, we represent every flat by a matrix vector pair. For a given ambient space, squared distance fields can represent flats of every dimension in a unified format. As they are just scalar fields, they can be scaled and added together, resulting in another quadratic polynomial. The resulting quadratic polynomial, however, will be the SDF of a flat only in some rare cases. Our method can be summarized as follows. It takes the matrix vector representation of a set of flats and computes their arithmetic mean, their geometric median, or any other LP mean, resulting in a matrix vector pair Q star and R star that represents a quadratic polynomial, but most likely does not represent a flat. Note that computing the mean or the median makes use of the fact that squared distance fields can be linearly combined. Then, we project the result of the first step onto the manifold of flats, by first computing the minimum of the quadratic function that will be an element of the new flat. This is done by just solving a linear system. Then, we extend the point by the span of the eigenvectors of the matrix Q corresponding to the smallest k eigenvalues. The dimension of the output flat that is given by the parameter k can be chosen by the user. The entire method consists of just matrix and vector summation, the diagonalization of a matrix, and a linear system that can be efficiently solved due to the diagonalization that is done before. At the end, we will look at the results of our archery experiment. The original arrows are highlighted in red. We compared our approach, indicated by blue arrows, with a method from a multi-view geometry in computer vision textbook, indicated by the green color. It is clear that our method produces better results than the rank minimization approach from the textbook.